actually called us and asked if he can speak to you guys today. How are we? All right?
Yes.
Perfect. Put your hands together. Give a round of applause.
Oh. Okay, hello everyone. My name is Howie, and this presentation is about engineering a better Java build tool experience. So the motivation for this presentation is that although the Java language is known to be very easy to learn, extremely performant, and have great IDEs, Java build tools don't always live up to that reputation. So this talk will explore what are the problems with Java build tools today, why are they problems, why are they so hard to solve, and explore some of the alternative designs or ideas that can make progress on these problems, one of which is one of my open source projects, which is a mill build tool. So about myself, I've been programming in Java for a bit over 20 years now. I've been working open source projects since 2012. My last job was at Databricks, which is a Scala JVM shop. So a lot of the projects are Scala running on the JVM, but also a lot of Java projects and other JVM related technologies. My professional work is all in developer tools. So dev environments, build systems, test systems, CI systems, and the whole laundry list of things that go on before production. So this talk will have 4 sections. We'll first look at can Java build tools even be better? What are the problems? Is there room to improve? And why is it difficult to improve on these problems? Why aren't they already solved? We look at Mill, which is one of the open source projects that I worked on in my spare time. It is a build tool that tries to explore the solution space of how can Java build tools be designed and how can it be better than they are today. We'll look at what makes Mill interesting. It's not just a build tool, but it's better than the existing build tools in some way. And one of the concrete ideas, which is the object-oriented builds that underlies this project, making it easier to learn than Maven or Gradle or other tools on the market. So the first section is, can Java build tools be better? This largely falls down into 3 categories from my experience. One is performance. Like Java is extremely fast. You compile things using Maven is surprisingly slow and have high latency. IDE support doesn't always work as well as you'd like. You can jump to definition, might always help you as much as it does in your application code. And extending the build tool, either configuring or programming it to do other things, is more difficult than you may expect, given what you want to do. So we'll go into these one by one. First, performance. People often don't realize how fast the Java compiler is because all the interactions with Java C are through the build tool. So, for example, if you look at the Netty project, Netty is an open source async networking framework, clients and servers that many of you probably use transitively in your code base. 500,000 lines of code, not a small project. Takes about 50 seconds to clean compile on my laptop using 10 cores. And I can show you this now and just kick this off in the background. So this turns off test, turns off check style, turns off other linters. I just want to benchmark the compilation. And it will take about 50 seconds, so we won't wait for it. And we'll come back later. So looking at a single module to try and narrow down the problem further, we'll see that Netty common, which is a common submodule of Netty, compiles at about the same speed, about 6,000 lines a second, so 30K lines, about 4.5 seconds. And in isolation, you don't know whether this is good or bad. Like people say Go compiles quickly, that Rust compiles slowly, 4.5 seconds for 30K lines of Java, what is that? And one thing we can do is we can take the module of Netty common and compile it without Maven. So Maven just shells out to Java C internally. So we can just copy the command which Maven logs in the terminal and run it ourselves. And we'll see that Java C compiles this module 3 times faster than Maven does. So already that's like a lot of overhead. The build tool kind of puts before and after calling Java C. The Java C in the middle is exactly the same, but just the setup and tear down for Maven actually adds quite a lot of overhead. And those of you who are experienced JVM developers might know that this is the slowest way you could possibly run Java compiler. Who knows why? So, warm up, yes. The Java compiler is a Java application running on JVM, and JVM is extremely slow to start, and after it takes some time to warm up and then gets very performant later. So by running Java C from the command line, you're getting the very slow part, you're never getting the fast part that then the process exits and you start again, it becomes slow again. And it's still 3 times faster than Maven. So to see how fast it can be if run properly as a long-lived Java process, we can run Java C in memory. And if we do so, we'll see that instead of taking 1.5 seconds to compile this submodule, it takes 0.3 seconds. So in theory, we should be able to compile the whole netty code base in 5 seconds on one core, but instead we're taking 50 seconds on 10 cores. So that's not how much overhead the build tool adds on top of the Java compiler. And you should see this live. So if I come back here, we'll see that it took about 50 seconds to clean compile in parallel the whole netty code base on my laptop. I'm just going to copy these commands since they're a bit long. So this is a clean compile command for only netty common. So I'm using compile rather than install, so there's no jarring, no assembling or anything, just compilation. And it compiles 174 lines. Maven says it takes 3.6 seconds, but actually takes about 5 seconds on the command line. Since there's some setup and tear down, that's not timed. If I run Java compiler on its own, it's a bit long, so people don't actually paste this into command line themselves because it's really tedious, but let's say I run it alone without Maven, you see it takes about 1.4 something seconds. And if I run javac in memory, and let me show you what I mean by that. So I have this bench.java file on the right. This is just a single file Java application. You run it using java bench.java. And it just calls the Java compiler API, javax.tools or Java compiler in memory over and over in a while true loop. This is just to benchmark at how fast does it happen if the process is allowed to get warm. So if I run java bench.java again with this long class path, you'll see it starts off not that much faster, but every iteration gets faster and faster because that's what the JVM does. So the optimizer kicks in, your assembly gets optimized, and after a few iterations, you'll see we are compiling the same 29,000 lines of Java, but we're taking 300 milliseconds at about 100K lines a second instead of taking 4.5 seconds. So it's literally 15x performance left on the table by the build tool. So the compilation is not the only thing you do in your Java workflows, but is this representative of how much overhead the build tool can add? Like the Java compiler is actually as fast as the Go compiler, any other compiler out there. It's actually very, very fast, and it should be basically instant to compile anything, even clean. But with the build tool wrapping it, it actually somehow feels a lot slower and not so responsive. That's performance angle. Let's talk about IDE support. So all Java build tools have IDE support, but IDE support, it might not be as good as you hope for coming from a Java background. So over here, I have the Mockito code base, where this is built using Gradle instead of Maven as the netty code base was. You know what Mockito is. It's the unit test mocking framework. And you see, I do have IDE support for this. There's some syntax highlighting and so on. But I can't always jump to things. I can't jump to error-prone javac, can't jump to libraries error-prone. I can jump to JVM args, but I get just a getter and setter. So in this case, I don't have the comments, but even with the comments, I just have getter and setter. It doesn't tell me what the value is before I set it, which is what I care about. Neither does it tell me where these values are used later. So if I'm setting something and something is misbehaving later, how do I debug this build tool? I really can't. So I can Google, I can Stack Overflow, I can ChatGPT, I can just try an error, but I can't really investigate and understand the build logic to debug it when something goes wrong. So when things go well, everything's perfect. When something goes wrong, you're often stuck, and that's the common experience working with build tools, whether Maven, Gradle, or even outside the Java ecosystem. So this is not the experience you get in any Java project. If I open up any random code in the Mockito code base, I can jump to any name you see in this file, any function, any variable, any class, and you expect to see something useful. So even if I don't read the documentation, or even if the documentation is wrong or out of date, I can always dig deeper using the IDE. So the difference between the build tool and the application code is that the application code is made of classes and methods that call other methods, and IDEs are great at exploring class inheritance hierarchies and method call graphs. Whereas if you look at your Gradle code, for example, it's made of global variables like JVM args. And just because you wrap the global variable in the getter and setter doesn't make it any less global or any less of a variable. And so IDEs are not good at working with global variables. If you use global variables in your application code, it'll also be very hard to understand and explore in your IDE. And that's why people don't do it. But because build tools like Gradle and others use global variables kind of extensively, you just cannot get good IDE support, even though you have the same IDE from the same company. And over here, I showed the Groovy DSL, but the Kotlin DSL also has the same problem. You can't really explore it, even though Kotlin has excellent IDE support when used in application code bases. So the last thing we're going to talk about is programmability. So ideally, if you just use the build tool, does everything you want by default, does nothing you don't want, and everything's perfect. But usually you do need to customize it to do something special. Like you may have a custom bill of materials, you need to deploy for security scanning, or custom deployment artifact that the new cloud vendor requires, or a custom linter that some internal team wants to try but other teams aren't confident in yet. So you always have to do something special, and maybe the Netty and Mockito code bases I showed earlier do special things because that's necessary for what they do. And any real code base usually needs to do something special as well. So as a kind of benchmark to show off how customizable things are, we're going to use this artificial requirement, which is to save the project line count as a line count txt resource file to be used at runtime. So this is a bit kind of contrived, but it's representative of many of the weird things that you have to do in a real project's build system. So this is not impossible. Using Maven, the answer looks something like this. It's not impossible, but it is kind of annoying to set up. ChatGPT can help maybe nowadays, or Gemini, but it's also pretty annoying to debug. And a naive implementation has many things that can easily go wrong. For example, you may forget to escape your ampersands because it's not just bash, but it's bash in XML. You need to escape ampersands as ampersand amp semicolon. Windows obviously doesn't work, so half your company wouldn't be able to use this build system if they're on Windows. And there are other ways to do this, none of which are as easy as you'd expect. So counting the lines of code in a folder recursively and adding it to a file as a number is like so trivial, anyone should be able to do it in 30 seconds without any documentation because it's so easy. But with a build tool like Maven or Gradle, it's often a lot trickier than that. Gradle has a different set of constraints. So Gradle is in Groovy or Kotlin. There's no Windows problem. It's all JVM cross-platform. But there are other problems, for example, needing to set up the correct dependencies and wiring up your build logic into the wider Gradle build, like setting up the input files, output files, do first or do last, which one do I use, depends on, making sure I register things in the right order. Gradle, the registration does depend on order and you can do it wrong. And it's easy to get this wrong. So in this case, which is like the simplest possible Gradle build extension, there is a bug that will make the build non-deterministically slower sometimes, depending what files you touch. And let's see if anyone in this room can spot it in the next 30 seconds. So some junior engineer sent this to you for code review, like here's a new Gradle extension, and there's a bug in it. Where's the bug? So the bug here is that I'm declaring a dependency on the source main input folder, but I actually only care about source main Java. So the output will be correct, it'll compute the line count correctly, but if I touch the resource folder, I touch source main templates or other source main anything else, it will unnecessarily recompute the line count. So for this kind of small task, it probably doesn't matter, but you can imagine in any non-trivial task, these bugs will just slip in, and if you depend on too much inputs, you get slowness. You depend on too little, you get flakiness where a task doesn't run when it should. You can't catch it in code review, or like 25 of you couldn't catch it, even though it's a really trivial Gradle extension. And that's how your build becomes slow and flaky over time as these bugs slip in. And even if you don't configure your build but use plugins, the plugin authors will have these bugs too because they are just people trying to configure their build in similar ways. And I'm not saying this is the best way to do this in Gradle. Gradle does have several different APIs you can use, but this is, I guess, typical of what you may find in the wild and what people may come up with when they are customizing their Gradle build. So that's the problem with IDEs from my perspective, from build tools from my perspective. Like the performance, IDE support, and programmability. For Java, Java as a language has great at all these things, but Java build tools like Maven or Gradle, it's a lot not so great. It's not impossible, but it's trickier, it's more tedious, it's more error prone, you'll get it wrong, and generally you'll end up having more difficulty. It's worth asking, like, why are these problems? Like, why don't people just make super simple build tools? Like, let's call Java C like I showed you from the command line earlier, or just download the jars using curl and whatnot. And the answer is build tools actually do a lot of things that people don't realize until you try a new build tool that doesn't have all these things, and then you realize that they're all missing. Things like parallelism, like I have 10 cores on my laptop, me waiting for my laptop with one core churning is a waste of time. Things like caching, because I already computed the thing 5 minutes ago, why am I rebuilding the jar again? Or I already downloaded the task, the jar has already resolved the dependency versions, why am I doing it again? So if you try to make a build tool naively, just like from the command line, shelling out Java C like I showed, you'll immediately hit upon the lack of all these things. And people will ask, why doesn't this work? And they won't use your new, faster build tool. But these things are quite complicated. You can imagine you want to make a user-facing API that exposes all this, it'll be quite a complicated API. And that's why build tools are complicated, because they need to deal with these complicated concerns, whether you know it or not. So that's a Java build tool, the better question. Like, answer is maybe there's lots of room to improve, but it's also not an easy space to work in. It's not as naive as just running JavaScript for command line and getting a 5 or 15x speed up. Next, we'll talk about Mill, which is one of my personal open source projects I've been working on for a few years. And Mill is a build tool that tries to improve upon to build existing build tools like Maven, Gradle, SBT, or other Java ecosystem projects. It's not a new project, but it's definitely not as big as Maven or Gradle. It's used by a few people. It's more widely used in Scala, but some Java projects use it. I know Netflix and Disney have some teams using it. So not zero, but definitely not a large group of people. It's like some people out there using it in some companies and some projects. So a simple Mill build looks like this. This is Scala syntax, unlike Gradle, which is Kotlin or Groovy, but hopefully it's not too foreign. So I have an object which extends a class. I have some method definition, which has some dependencies in the Gradle format, and I have a nested test object which has support for JUnit 4. It has packages, has imports, comments, all the normal JVM things. So this build here, I can use foo.compile because foo is an object, so it's a .compile method. I can do foo.run, foo.test, foo.assembly, and run the assembly later from the command line. So far, nothing unusual. You can do all these things in any other build tool as well. Just to go a bit further, this is a Spring Boot application, Hello World, or to-do MVC application built using Mill. I can show you this one live. Let me pull up the right terminals. So here's the code. You can see it has a lot more dependencies than the Hello World we saw earlier. It has all the Spring Boot starter stuff, JAX-B data binding, web jars, H2 for in-memory testing, and a separate integration test with test containers, Postgres for integration testing. And this example, which is on the documentation page, you can just run it from the command line. So I can do, for example, /mill test. I can run the test in the code as well. Like I can run the test here from IntelliJ. I can, while that's running, I can do mill -- watch. Let me see what the command was. Test.run background. So this will run it interactively on localhost 8087. So if I go here, this is my to-do app. I can make changes. For example, I can change the templates to say like hello world, and it will get picked up. Spring Boot will restart, and then I'll get updates. So just showing you how this works with Spring Boot, kind of a more interactive end-to-end scenario. So people will often ask, like, what does this support or not support? And as a first approximation, it supports most of the open source Java projects that are widely used. So it doesn't support some of the more niche ones. Like it doesn't have Google Web Toolkit or Vardin or some of the other projects like that. But think the basics like auto-formatting, linting, code coverage, publishing to Maven Central, now soon Attack Central, the different web frameworks generally work. And different languages as well, including like Kotlin or Scala or Android or whatnot. So that's like a lightning tour of the Mill build tool where it does everything the same as the other build tools. So that's not so interesting. The next part is, I think, maybe more interesting is where Mill is able to improve upon the other build tools. So this, again, goes back to the 3 buckets I saw earlier. There's performance, ID support, and programmability. And again, we'll go through them one at a time. So from performance, we took the Netty code base, which is normally built using Maven, and we ported it to Mill, just like copy-pasted the build files, changed the syntax from the XML syntax to the Mill build syntax. It's not a small project. It's like 500,000 lines with 50 submodules. So it took about 2 or 3 days to port. Not a long time, but it wasn't trivial. And we compared the builds on both sides, running tests that all passed, compiling everything, and so on. So I guess the thing we noticed is that across all the benchmarks, Mill is a lot faster than Maven to do exactly the same thing. And we can show it. So this parallel clean compile benchmark is what we saw live just now on the Maven side. I can show the Mill command here. So if I go back here to Netty and I do /mill clean and /mill compile, the first time may take a few more seconds because Mill is a JVM program, so it may be cold. But it still should be much faster than Maven to compile the Netty code base. You can see all the things it's doing in parallel while it's working. First time it runs, it'll take about 15-20 seconds, I think, normally. Yeah, so 18 seconds. If I run it again, it should take about 10 because the JVM running in the background will have warmed up by now. Okay, yeah, 11 seconds to compile the whole netty code base instead of 50. So this is quite interesting because it's still pretty far from what we should hope for. Like Java C should compile everything in 5 seconds on one core. I'm still compiling it in 10 seconds on 10 cores. But it just shows that it is possible to get a lot more performance out of your Java build tools, even using the same Java compiler, than you can get out of Maven or Gradle. And other things like incremental compilations are also a lot faster. So if I go to my netty project and I change a single file, let's say I change a random test suite and add like a comment here, hello world. Using mil, it's much quicker at detecting that it needs to do nothing. So let me just run this again. So first I compile everything. So this is again first a clean compile. Then I'm going to change my code by adding another comment. And if you run another compile, it notices it has nothing. It has only one file to compile and exits in about 2 seconds. Whereas if I do this with Maven, /maven w without cleaning, so this is compiling everything, but it should have almost nothing to do, right? I only changed one file to add a comment. You'll see that it still takes quite a long time, and there's only one file that needs to compile, and there's no change to bytecode. There's really nothing that needs to happen. The class files are the same, the jars will be the same, but Maven isn't quite smart enough to realize that and exit quickly. It compiles lots of files in every module rather than just one file in one module. So that's the performance angle compared to Maven. For Gradle, we did a similar comparison using the Mockito code base again. Again, it's a non-trivial project, 20 sub-projects at 100K lines, ported it to Mil from, in this case, from Gradle, and complete enough that all the tests pass. And the numeric difference is not as big as with Maven. With Maven, we are seeing like a 5x speed up. Gradle, we are seeing about 3x speed up. So at a first glance, you'd say that Gradle is maybe 2x faster than Maven, and I think people who've migrated from one to the other can probably vouch for that. But there's still a lot of speed up that Mil is able to take from here, and I guess even Mil is pretty inefficient compared to how fast a Java compiler really should be running at, if used correctly. So compiling is not everything. There's some other features that I think are quite neat that we built for ourselves that I think other people find interesting. One is selective testing. So you can, for example, ask Mil to take a snapshot on the main branch, take a snapshot on the pull request branch, and ask Mil, hey, what test suites submodules change or were downstream of my changes, so I can run those tests. And you can even ask it to render like a tree structure. Here's like this is the folder that changed in the Mil like syntax, which affected this, which affected this, which affected this test suite. So you only need to run this one test suite rather than all the other test suites in a file on this pull request in a project, which in a big project where you're usually changing small parts of it can be very handy and save you a bunch of time and money. Incremental assembly jars I thought were quite neat. So making big assembly jars like this 200 megabytes Spark Submit assembly is naturally quite slow. You're zipping and compressing 200 megabytes of jar files, which are already zipped and compressed. But updating an assembly jar can actually be very fast. Mil is able to do it in 1 second after adding a new file rather than 20 seconds because assembly jars are just zips, and it's actually very easy to take things out of zips and put new things in. So Java provides that functionality built in via the Java NIO zip file system. And Mil just uses that to reuse existing assembly jar and just incrementally update that with new class files or modify class files as you develop your assembly. So that saves a bunch of time, and I don't know why the other tools don't do it. The last thing I think is worth mentioning is the Chrome profile. So every Mil command you run from command line generates this profile that tells you where the time is going. And I can show you this now. So I'm going to run another clean compile because just now the last compile is very fast, wasn't interesting. So it's doing a big clean compile, doing a bunch of stuff. And in the code on the right, in the output folder, you'll see there's this Mil Chrome profile.json. So this is not human readable really, but it's a standard format that the Chrome team at Google publishes that is supported by the Chrome tracing app. So all of you who have Chrome have this profile visualizer in your Chrome browser already at chrome://tracing. And if you generate JSON that just contains the names of the tasks, when they start and when they end, or how long they take, you can take this JSON, dump into Chrome, and immediately get a 2D visualization of where my time is going. So earlier we saw it took like 10 plus seconds to compile the whole netty code base in parallel, 10 cores on my laptop. well, here's what the 10 cores are doing at each point in time. You can see where they were fully saturated. You can see where they were bottlenecked on common compile. You can see where they were bottlenecked on microbench. You can see there's a whole bunch of compilations here that kicked off by, let me click on this. They got triggered by transport test compile. So clearly all of these guys are waiting for transport test to complete, which was waiting for transport test super to complete before they could start. And even if you know nothing about MIL and know nothing about the Netty code base, you already have some good idea of where the time is spent. Why is it taking 10 seconds to compile? And if I want to do something, what can I do? Like maybe I can break up microbench into smaller submodules so you compile in parallel. Maybe I can break up common so there's a smaller common that people can depend on so they can start earlier, and so on and so forth. So this is possible using other build tools, but it's usually less convenient. Like Maven, I think, has a plugin that spits out a command line like log that shows you in milliseconds or seconds how long the tasks take. Gradle, I think you have to pay for Gradle Enterprise and give them your credit card, set up a self-hosted Gradle Enterprise dev velocity server to upload your build scans to get this UI. MIL, you just get the JSON file for every single command, whether compile, test, publish, whatever, dump into Chrome that you already have. You all have Chrome, and you can see exactly where the time is going in your build. So that's a performance angle where I think MIL is pretty interesting. The raw performance is better, which I think is quite cool, but also has a bunch of these features that we built for ourselves as people using MIL. And it's nice to be able to see where your time is going when you're waiting for a long build or long test to finish. Next, let's talk about ID support. So to compare this, I'm going to open up the Mockito code base with Gradle on the left and the Mockito code base with MIL on the right. So I'm going to go to the equivalent parts of each project. So make this a bit bigger. So the first thing you may notice is that the Mockito code config for MIL on the right looks very similar to the one for Gradle on the left. And that's kind of expected because both build tools, you need to set the correct add exports flags, make the test pass. You need to set the correct compiler flags, and so on. You need to set the right dependencies. For example, both of them have the error prone submodule of Mockito depending on the Mockito error prone test API, depending on the error prone library externally, and so on. So all of this is the same. In MIL, it's spelled a bit differently using this def equals syntax, but it's basically the same information. Where things diverge is where in Mockito Gradle, you kind of jump to definition and get these global mutable variable getters and setters that don't give you any information. With MIL, you configure things rather than using global mutable variables. You configure things by using method definitions. So def is a Scala syntax that MIL uses for method definition. And you can see that even IntelliJ knows that this is an override method that overrides an existing method. You can jump to the original method that got overridden. You can see its Javadoc. In fact, you can even ask for its Javadoc here. IntelliJ is able to give you, whereas you can't do that in Gradle. And you can navigate this kind of these tasks exactly as you navigate any application code base. For example, I fork args. I can see where it's called. It's just a method. So fork args gets called by runner. Runner gets called by run background task. Gets called by this deprecated thing we can just ignore for now. Gets called by run fork task. Run fork task gets called by run. So just like that, you can see, you can trace the data flow of I'm setting this key, what actually ends up happening in the task I care about. I set fork args, but I actually care about what happens when I run the code. How do they affect each other? And with MIL, you can trace it through just like an application code base using your IDE, because they're just methods. And you can I showed you tracing downstream. You can trace upstream as well, like find main class. I don't know what this is. I can jump to it. There's no Javadoc, and it might not be documented online, but I can look at the implementation, and I can jump to this as well. In this case, I can see that this find main class opt thing calls main class, which is jump to defined up here. This is if you explicitly set a main class for the project, sub-project, and all local main classes if there's no explicitly set main class. I can jump to that here and see that this uses class graph, which is another JVM open source project, to scan the class path to look for a class with a public static void main signature. So none of this is something that's rocket science, but really just takes the user experience in the IDE that you see every day in your application code, in Kotlin, in Java, in Scala, even nowadays in TypeScript and Python with Python type checking, and brings it to your build tool. And it's able to do that because rather than using global mutable variables to configure your build, and most other tools do, MIL uses methods, and IDEs like IntelliJ are very good at navigating methods and classes. So that's IDE support angle, where I think MIL is quite interesting and works very differently from other build tools. Lastly, let's talk about programmability. I think the most interesting thing here is that while most build tools require you to publish a plugin or extend it using a plugin, Mill lets you just write code and use libraries from Maven Central directly. So we'll see what that means. I'll also do this live. Where is my example? Recent custom Java. Okay, here's my example. Might take a moment to import. So on the right here is the minimal Mill build for a simple Java application. You'll see that there's object foo extends Java module, and there's nothing in it. And that's because it's like Maven or Gradle. It has default for everything, like default source folder layout, default resource folder layout, default this and that. And so if you really don't need to customize anything, you really just get all the default methods inherited from the Java module class and nothing else. You don't need to define anything. And I can already take this custom java./mill foo.compile to compile the foo.compile to run the foo.compile task, which is inherited from the Java module superclass. So let's say we want to do what we did earlier, which is count the lines of code in this module. So in Mill, the way you define custom tasks is by methods. So you can do def line count equals a task. And within this task body, you can call other methods. So we can see all the different methods that we have available on the full Java module. There are many of them, so it's a bit complicated, but you get IDE support to see what you want to call. Like, do you want artifact name? Do you want all? In this case, I want all source files, which is the individual source files in the project, and I can map it. Goes to file.path. Use this file system library to read the file path, get the size, and sum them up. So that's all you need to do to define a custom task using Mill. It's almost like writing SQL. You take the thing, you map, sum, and you're done. And I can now do Mill show foo.line count. If it needs to recompile the build, this might take a second. 17, which is the number of lines of code I have in this small example project. I can do Mill inspect foo.line count. You can see we automatically capture the Java doc for you, so it's quite convenient. You don't need to copy it yourself. You capture the method calls for you, so we know that you called foo.all source files, so we can just track that as a dependency, so automatically rerun this if foo.all source files changes. And what we haven't done yet is we haven't wired this into a resource file. So in Mill, you already have a resource task on disk. There's actually several, but we can see which one we want. We probably want foo.resources. And the way you customize the existing task or method is by using object-oriented overrides. So I can use override def resources. Again, you get IDE support here. I'm going to override it as a task. I call the super resource method. And I'm going to write to this task.destination folder, which I'll explain in a moment, my line count.txt file containing my line count as a string. And then I will append to my resource path. This is using Scala syntax, so this ++ might look a bit unusual. A reference to this task.destination folder. So what's this task.destination folder we see here? What this is if I show it to you on the command line, you'll see that resources, foo.resources now has two folders. It has foo/resources, which is a source folder, which is now super resources. And but it also has this out/foo/resources.des. So Mill puts all its output in the out folder, and you can see that we have this destination folder here corresponds to this task.destination folder here. So we do this because putting stuff in the target folder in traditional build tools like Maven, Gradle, SBT is always very fragile. You don't know who's putting what in what path. Some plugins may conflict with each other by taking the same path. You don't know what you can safely delete when you're cleaning things. You don't know what some task is still relying on. And generally, you don't know what's doing what because the file system is a huge global mutable variable. Anyone can write anywhere, and you don't know who's writing to where or reading from where. So with Mill, we try to solve this by giving every single task its own unique destination folder. Foo.resources gets out foo.resources.des. Other files like foo.compile will get compile.des, assembly.des, and so on. And they're all guaranteed to be unique. So this means that our global mutable file system becomes a local mutable file system. And because you're only allowed to write your own destination folder, not allowed to write to other people's destination folders, it becomes a local immutable file system. So that is much easier for Mill to deal with. Like Mill knows where things are. Mill can delete things automatically because it knows where things are. Mill can reuse data automatically because Mill, again, knows where things are on disk. And now that I've done this, I can just look at my destination folder from terminal. I can see it's line count.txt. I can see the contents. It's 17. I can do mil foo.run. And output 17. So I think this is quite interesting because there's no line count plugin, there's no exec plugin. Doesn't feel as awkward to configure as bash, as writing bash in Maven, exec plugin, or writing Groovy or Kotlin in Gradle. So although Scala and Kotlin are quite similar languages, the APIs exposed here are very different from the Kotlin APIs. They don't require as much boilerplate to set up and don't require so much like manual wiring of I depend on you, I'm writing to here, I'm writing to here, all of which has opportunity for mistakes. So let's take this one step further and say rather than just having a line count as a text file, I want to pre-render it as a HTML template. So this is a bit contrived, but there are many cases where you want to reuse a third-party library in your build system, third-party code generator, third-party linter, third-party this and that, artifact publisher. So how do you do this in Mill? So in Mill, you do not have libraries like TimeLeaf plugin built in. I can't say import org.timeleaf here because it's a build tool, it's not a web server. But what Mill does have is a syntax to say import $iv, and then I can import org.timeleaf with the Gradle coordinates, timeleaf 3.1.1.release. So if I then ask IntelliJ to reload the build, this will take a moment, but not too long because I had timeleaf cached earlier in my local M2 cache. You'll see it now, it resolves timeleaf. I can now see timeleaf available on my external libraries tab in IntelliJ. And I can start importing things. I can import the timeleaf context. I can import the timeleaf template engine. And I can start using it. I can explore the code. I don't know what timeleaf template engine is. Well, go look at the code and see what it is. Feels just like working in an application code base. So I can define a new method, def HTML snippet, which is a task. And I'm going to say var context equals new context. And I'm going to say new template engine dot render dot process. I need to give it a template, which I'll just copy from the slide because the timeleaf syntax is a bit finicky with escaping and so on. So let's copy this. I'm going to say context dot set variable heading to line count as a string. I need to pass the context in here. Or maybe I need to do it the other way around. Other way around. Okay. So now I have HTML snippet task. I can do mill show foo.html snippet using its normal like object-oriented selector. You can see it's rendered here. I can open it up on disk in the out folder. So out/foo/ there's a bunch of tasks. I want HTML snippet.json, and you can see the value here is cached along with some hashes, so Mill knows when to invalidate the cache. And if I wire it up into my resources task, I can do mill foo.run. I can see that I'm now pre-rendering HTML at build time using a third-party library, the same one's used in production. I can access it at runtime. And throughout all this, I didn't have any plugins. So if I want to use timeleaf, I didn't have to go find a timeleaf plugin or a line count plugin or an exec plugin. I want to use timeleaf, I just use timeleaf. I import it here, I import timeleaf, the classes, and I just use them as part of my tasks. And in Mill, the tasks are just methods. So you can just write your method body here and it just works. Again, the syntax is Scala, but it looks relatively similar to any Java you'd write. Maybe you don't have any semicolons because they're optional. So that's the extensibility angle where I think Mill is quite interesting. It's different from other build tools. So if you compare like the Mill code versus the Maven code that we saw earlier, the first thing is that both of them contain imperative logic. Again, in the ideal world, your build tool will be purely declarative, but sometimes you do need to customize things and either customize it yourself or some build tool plugin author will customize it for you. And in this case, both of them have the same logic. They both count the number of lines and put into a file, one using JVM Scala code, one using bash code. And just because we write the bash code in XML doesn't make the bash any less fragile or any less like error prone. It's still bash, it's still a bit scary to work with. And it makes sense, you don't want to put too much logic here in the bash. You don't get ID support, you don't get type checking, that has poor performance, not cross-platform. But all of these problems are solved in Mill because you do get type checking, you do get ID support, it is cross-platform, runs on the JVM. And so some of the kind of traditional reluctance to put things in your build tool or customize your build tool really just goes away because it's no longer so scary. It's just like writing application code, just you write it in your build and it gets cached and parallelized automatically. Compared to the Gradle code we saw earlier, again, the business logic is the same, and the business logic in both cases isn't really the hard part about Gradle. Like, if I give anyone who's learned Kotlin 101 the task to read lines from files and write them to a resource text file, anyone can get this code out without too much difficulty. But this is not the error-prone part. The error-prone part is generally all this other stuff that no one learns in school, no one learns in Intro to Kotlin, but nevertheless, you need to get all this stuff correct before your Gradle build can work. And sometimes the Gradle build works even incorrectly, just more slowly or more flakily than you'd expect. So with Mill, we still have the same business logic, or rather, I'll call it build logic, and maybe might be a bit more concise than the Gradle equivalent. But what's interesting is we automate all the other stuff. So you call all source files, we know you're depending on the source folder and its files. You call line count in resources, we know resources now depends on the line count task. You call super, we know resources still depends on the original super folder. And we do all this for you, so you don't need to wire it up using depends-ons and input files and output files and so on. So you really get the pure build logic here that actually is quite simple and easy to write without all the error-prone kind of wiring that traditional build tools often need to do. So that's a programmability angle where I think Mill is very interesting. So those are the improvements where I think Mill kind of shows some promise over the existing build tools. It's not as battle tested over the last 20 years as Maven or Gradle is, but as a newer project, it has quite a lot of cool features. Better performance, better ID support, surprisingly, and even easier extensibility with ID support and type checking for any extensions you write. The last thing I'm going to talk about is one of the interesting ideas of Mill is the object-oriented builds. So the other things are things that maybe other build tools can copy, right? Other build tools can easily run Java C hot to get warmer. Other build tools can easily set up incremental assembly jars or selective testing. They already have the build graph. But object-oriented builds are something that's quite unique to Mill that's worth mentioning. And we touched on it earlier already. So one of the things that every build tool needs to do is to define templated, customizable graph computations. So this seems a bit sophisticated, but we've taken an example. Like I have 3 modules, foo.bar, foo, and bar. Foo.bar is dependent on by foo is dependent on by quux. They all have sources, they all have compile, but foo.bar.classPath is used by foo.classPath, which is then used by quux.classPath, but foo.bar.classPath doesn't depend on anyone else. So this is what a typical build graph looks like for any multi-module Java project, which is any, and it needs to be templated because all the modules look almost the same. It needs to be customizable because they're not actually the same. Like there will be some tweaks here and there, like class path, this class path not having any upstreams, where these class paths having different upstreams. It needs to be a graph because we need to know what order to run things or what we can parallelize. And we actually need computations to do the work. Like we actually need to have someone calling Java compiler or creating the zip file using Java NIO zip file system or whatever. So if you think about it, trying to define an API to have templated customizable graph computations can easily be very complicated. A naive API will look exactly like what we have in Gradle, where we have a computation and we have a bunch of graph wiring up here, like input files, output files, depends on, to wire up the customizable graph with a computation we have here in the middle. And even if you don't do this yourself in your build, if you're using plugins, the plugin authors have to do this, and the plugin authors, if they have trouble, they'll get it wrong as well. And we saw how easy it is to get something wrong in Gradle, where our wiring was slightly off. And so your plugins will then become slow, or your plugins will then become flaky, and you'll be using plugins and making your build slow and flaky, and you have no idea why, and neither the plugin authors, because it's so hard to get all this right correctly. So Mill also has to do all these things, but what Mill has realized, what we have realized working on Mill, is that everyone already has a way to define templated customizable graph computations. It's called object-oriented programming, where you have methods calling other methods that forms a graph. It's called a call graph, but you can use it as a build graph. If you want to template this method call graph, you have a class and multiple instances of the class. And if you want to customize one of those instances, you just override the methods, whether using a subclass, using an anonymous instance, whatever, and you override the method or even multiple methods with new implementations. And the method bodies, which actually run code, those are the computations. So actually everyone already knows a way to do this, and it can be drilled into for many years, but Mill actually tries to use this to model your build system, and that's what's special. So if you look at this example, hello world Mill build earlier with nothing in it, is literally a JVM object extending a JVM class, and like any other JVM object extending a JVM class, you inherit all their methods, and these methods already call each other in some kind of call graph data structure. So when I define a new method, although the syntax may be a bit unfamiliar since it's Scala syntax, you already are familiar with the meaning of this. I have a new method that calls all source files. I'm overriding resources that call super resources and line count. And even though override and super are quite subtle concepts sometimes, you already know how this affects a call graph because you learned override and super 20 years ago in school in the first year of computing class. So once we have this graph, Mill is then able to do things like parallelize the parts which don't depend on each other. So like compile and line count can run in parallel, and assembly needs to run after the other two because it depends on them. Mill can assign things command line names, like foo.linecount can be called as foo.linecount from the command line. Foo.compile is inherited, so you don't see here, but foo.compile exists, as you know, so we call it foo.compile. As well as assign them all unique folders on disk for caches. So foo.linecount gets out foo.linecount.json. Foo.compile gets out foo.compile.json, and because it writes to disk, we make it write to out foo.compile.dest. And for example, assembly goes to assembly.json, assembly.dest. They're guaranteed to never collide with each other, so you don't need to worry about coming up with unique names that's unique across your whole build system and all upstream plugins. Lastly, Mill is able to do automatic invalidation. So if I touch a resource folder, which is now full super resources because I overrode it, Mill just does a breadth first search, sees that resources is downstream, needs to recompute, assembly is downstream, needs to recompute, and compile and line count are not downstream, so those can be reused. Furthermore, foo knows when it wants to recompute assembly, it knows where to delete the old files for you because it knows that it's at assembly.json, assembly.dest, standard paths on disk. And when Mill wants to reuse compile and line count, it also knows where to fetch that data from. The metadata being at linecount.json or compile.json, and the file data, like class files, being at compile.dest. So again, what's interesting here is that there's no code here related to dependency tracking, parallelism, caching, and validation. You don't see depends on input file output declarations. You don't see threads or locks or futures or semaphores or whatever. You don't see cache key computations or cache invalidation or reading writing to disk as caches. All that is done for you because Mill is able to restrict what you can do to these small computations. Mill is able to do the caching and invalidation and parallelism completely on your behalf. You just write your build logic basically as exactly what you want to say in this object-oriented style with classes, methods, overrides, and supers. So if we go back to this big list of why are build tools complicated, Mill also has to do all these things. We also have parallelism, we also have CLI, we also have custom tasks and caching and file tasks that write to disk and pass data back and forth and repetition and all that stuff. But Mill is able to reuse concepts you already know to answer many of these questions. So like who depends on what, runs in what order, what can be parallelized, that all comes from the build graph, which is a method call graph, and you all already know how method calls form a graph as they call each other. You already know how methods pass data to each other in their return value. Each method that gets called returns a value that caller can use it to do stuff. So that's how they pass data. You already know how to define methods. The syntax is a bit unusual, but they're just methods running on the JVM. And for the things that aren't answered by the method call graph, they are answered by the object-oriented nature of the Mill build. So the idea of foo.compile as the name of the object foo with the method compile. The foo.compile.dest similarly comes from that. The idea of if I've repeated modules, let's say I have 5 modules that are all similar, I can define a class, such as Java module, and instantiate that class 5 times. And if I want to customize any of those modules, I can override the methods, one or more of the methods in those modules, or even define a subclass that overrides methods and inherit from the subclass. So because you already know all these things, it's no longer so scary. Like you don't need to learn a whole separate way of customizing your templated customizable build graph. You can instead just use your standard methods, calls, classes, objects, and overrides that you've already been using for many decades in your application code, but now using it to work in your build code. And this is also why your ID support seems to work so well just now, because IntelliJ is very good at working with method calls and classes and overrides. So it's able to work with Mill builds just like it works with any application code base. So that's the last main section, which is the idea of object-oriented builds. While the other things like performance and stuff, I assume the other build tools will eventually catch up, may take hopefully sooner rather than later. Object-oriented builds are really core to the idea of how Mill structures a build and how Mill makes it easy for anyone with the object-oriented programming background to understand and navigate them, including tools like IDEs. So this is the last slide, just to sum up. I guess there may be 2 halves here. Like the first half is that there really is a lot of low-hanging fruit in the Java tooling ecosystem. Things like keeping a long-lived daemon to keep your your Java C compiler hot, so you can compile 15 times faster than Maven currently does. So I know that they're trying to do this with Maven D and other projects that are trying to land this kind of functionality, and hopefully it'll land sooner rather than later so everyone can benefit. Other things like incremental assembly jars, selective testing, all should be straightforwardly implementable in these existing build tools. I'm sure many companies have already implemented them internally, and ideally the build tools should just provide it externally because everyone wants this kind of thing. The second main point is if you want to try something new, or you have some side project you want to try out a new build tool, or you're tired of waiting 5 years for Maven to get faster, you really should try out Mill. I think it has a lot of interesting core ideas, especially this idea of object-oriented builds. And unlike many other build tools, these core ideas really translate into concrete improvements. Things like 3 to 6x speed-ups, things like better ID support, which is something that most newer projects have, or even the older projects all have problems with. Things like being really easy to extend your build code with code and libraries from Maven Central, rather than having to depend on some half-maintained plugin from GitHub that was last updated 5 years ago. So these are all things that the existing build tools have really struggled with even over the last 10 or 20 years that Maven or Gradle have been in active development. And Mill, despite being a much newer project, really has made concrete steps here to make it better. So the website is here, millbuild.org. You can go see, there's a lot of docs for it supports all the different languages like Java, Scala, Kotlin. All the examples are downloadable. You get a zip file, you can run it on your computer, try it out with instructions on what commands to run to see what they do. And that applies to every single example here, like whether Spring Boot or Micronaut or Gradle native image. You can just download the example, run the bash commands, and it should do what it says here because these also double as our integration tests. So that's the last slide, and I'm done. Thank you for listening.
Thank you. Any questions?
Yeah, I got a question. Could you present how is it possible to use already existing, for example, Maven plugins like, I don't know, FaceAce, Surefire? Does Mill support it, or has the alternatives for such plugins, how it might work?
We cannot directly reuse a Maven plugin, so usually there are a few options. One is it might be built in. So for example, Mill has built-in support for JUnit 4, 5, code test, Scala test, all different testing frameworks, TestNG, and it has built-in support for test parallelism and other things, so you don't need to use Surefire for that. Two is some plugins are wrappers for external projects. For example, a Scala PB plug or Java PB, Java Proto plugin, whatever we call it, Proto C for Java plugin is a wrapper for the open source Proto C from Google, and you can just use Proto C directly in Mill, just like how we used Timeleaf earlier. And the last case is for things that are not wrappers of external tools, but logic is really bundled in the plugin. And in such a case, you really just have to kind of separate out the Maven specific part from the core logic you care about. So whether it's like Maven config versus a Docker config, and you can use the Docker config just as a jar like we saw earlier, or like the Maven config or the linter, Gradle config or the linter that actually does a linting of your code, and take the linter and use that as a jar. So for the Maven plugins, usually there's some path forward, but it's not always trivial. And for internal plugins, you usually will have to rewrite them because we don't know what your internal plugins are. And
okay, understood. One more question, if I can.
Sure.
Did you already try, because programmatic support, like the IDE support, is extremely important from always. But nowadays, there is also one more thing important: how the Gen AI is actually supporting generating the code, the migrating. Did you try it, or did you verify how actually, I don't know, GPT, Gemini, anyway, any AI gen models are actually able to correctly generate some nil code?
I have not. I expect it will be worse than Maven or Gradle just because there is less training data out there. But hopefully, if people use it, there'll be more training data and they'll improve over time.
Okay, thanks.
You mentioned that you tried to compare Mill with Maven or Gradle. Have you come across other build tools and maybe compared to performance? For example, the Google's Bazel and stuff.
Sure. My experience is, my background is build tools, so I haven't done a head-to-head comparison, same code base with two tools, Mill and Bazel. But I did maintain the Bazel build for 7 years at my last job, since 2017 when Bazel was at 0.3. Compared to Bazel, I think Mill is a lot easier to use. Setting up and running and maintaining a Bazel build, my experience is that's been a full-time job for 5 people. So if you have a 5-person team, your whole team will be maintaining Bazel. That's not good, but if you have 100 people like my company did, then 5 people maintain the build tool, so everyone else becomes acceptable. So generally, if you're a big company that can spare the expense of setting up and using Bazel, and you become quite big, then Bazel becomes necessary, because Bazel provides things like every build task runs in an LXC container that cannot use up all your CPU, cannot use up all your memory, and cannot like mangle your file system, which doesn't matter for a small project, but when you have 1,000 people with 200 interns doing stupid things, it's very important to have these controls. But the downside of Bazel is that my experience with Bazel is that it's extremely complicated to set up and use. My last 2 jobs both migrated to Bazel. Both were a 1-person decade engineering effort, so about 3 to 4 people times 3 to 4 years to get Bazel set up and rolled out for everyone. So very powerful tool, especially for big companies and big projects which need it, but also comes with a very big cost that I think Mill is much easier to use. So you can use Mill as a 1-person project, whereas using Bazel as a 1-person project can be pretty dicey, even though I've seen it done.
Okay, but you kind of mentioned that, I was asking more of speed-wise. You were comparing these builds mostly speed-wise, and I'm asking whether, have you compared this also with Bazel?
Sure. Speed-wise, we don't have a head-to-head comparison. I expect that at the low end, it will be faster. Bazel's LXC containers for every build step does add a lot of overhead, and Bazel's not as optimized for low end. At the high end, Bazel will definitely be faster if you have a 20 million line code base that you need to compile very widely parallel. Bazel, for example, lets you compile it on the cluster and aggregate the results back. So Mill can't do that. So I think for smaller projects, especially 1-person projects, Mill is actually very fast, and I can show you this now, right? So I can time foo.compile when there's nothing to do. It takes 0.13 seconds to run. We use Gradle native image and some other fancy stuff to try and make it faster. Bazel will have some more latency because that's what Bazel's not optimized for this kind of small project. Bazel's optimized for huge projects, where a normal project that normally take 2 days to compile using Maven may instead take an hour or 20 minutes to compile using Bazel, because you're able to really aggressively parallelize it and distribute the computation. Yeah, hopefully that answers your question.
In my understanding, Mill is an imperative build system. Did you consider use declarative configuration?
Yes. So I think the main thing is that when the build is very simple, whether you're imperative or declarative doesn't really matter. Whether you just have methods that return strings, especially for the Mill Scala syntax. If you just have, for example, if you do def jvm id equals like Temurin 17, whether it's YAML or whether it's this Mill Scala syntax really doesn't really matter. It's just as short and concise. And the problem with declarative build systems is that once you want to customize things, you end up having to push things into plugins, which ends up being quite a lot of indirection. Or you need to do funny things in your declarative code, like bash embedded in XML. And this is not just for build systems, but for things like GitHub Actions, which are YAML. You end up having this like programming language in double curly braces in your YAML code. Same thing happens for Kubernetes templated with Helm. You end up having YAML is declarative, but you have these code snippets in this poorly defined interpreted templating language. So my impression is that when it's really small, it doesn't matter whether it's declarative or imperative. Like the default build looks like this in Mill, and whether it's YAML or not, it looks about the same. But when things get a bit messier, having it easy to just write code to extend your build, that really does lower the barrier to contributing versus having to define a separate plugin using a separate plugin interface. And then when the plugin misbehaves, you need to jump from your YAML file to your plugin and back and forth, or from one plugin to YAML to a different plugin's code base. So I think that's a trade-off. You could go either way, and Mill currently is, I guess, imperative or config as code rather than config as data.
Any other questions?
Cool, going once, going twice. I guess we are done then. Thank you very much for listening.